In today's modern age, it is very important to stay anonymous because you never know what people will do with your data. However, there are some people that don't really care about it, one of them being me. Now, in today's episode, we'll be talking about general chemistry. Now, I'm aware that this is my usual format where I have my whiteboard and I'll be jotting down everything and explaining it to you. Unfortunately, I do not have any whiteboard markers with me. So, I'll be just explaining some terminologies, and then after that, we're going to shift to a pen and paper for all the equations that will be needed. I will be listing graphs and possibly visual aids just in case, but this is just going to be me yapping for the next few minutes. Okay, anyways, so we'll be learning about kinetic molecular theory. Now, this is a theory that states that matter, which is composed of particles, are in constant random motion, meaning these little bits, these atoms, subatomic particles, are just zooming about in every direction and any direction. Now, before we move on to this, there are some basic principles to consider. One, matter is composed of small particles, atoms, the smallest unit of matter, technically. Second, particles are in constant motion. They are always moving. None of them are just static. They are always in constant motion. Third, particle motion increases with temperature. The higher the temperature, the faster they get. And here is a pressure formula for you to find out. Or here. I don't know where it is. Next. There are attractive forces that exist between particles. These could be intermolecular forces or like cohesion and adhesion, which we'll talk about later on. Fifth, collisions between particles are elastic. They're like rubber bands. They're elastic, right? Sixth, they have specific properties of volume and space. For example, this graph here, or image, explaining solids, liquids, and gas. You can see that some are rigid, some aren't rigid, some have a fixed shape, some don't. You get to see all the properties here. Now that we're done with that, we can move on to water. Specific properties of water. Now, one of them being the high specific heat capacity. It just means that water can absorb a lot of heat before its temperature increases. So let's say it can absorb X amount before it raises to a really hot temperature. Same thing with high heat of vaporization. It can absorb, or rather, it requires a significant amount of energy before it vaporizes or changes into a gas. Third, high heat of fusion. Again, you need a lot of energy, but instead of it turning into a gas, it's turning into a solid. Fourth, cohesion and adhesion. So this refers to intermolecular forces in somewhat. Basically, cohesion it refers to the process when two similar molecules stick to one another. So if you have two water molecules, they'll stick to one another. You have two of the same, two hydrogen, two whatnot. As long as they're the same molecules, they'll stick to each other. Adhesions are when those molecules stick to other surfaces. So if water were to stick to a table or water was to stick to wood, that's adhesion. So molecule to molecule of the same identity is cohesion. Molecule to a different thing, that's adhesion. Fifth, surface tension. So this is the elastic force we were talking about, but apply it to the surface of water. Have you noticed that when you were to fill up a glass of water, imagine this is being filled up, there is a point where the water seems to go past the top and it doesn't pour out. That is surface tension. That is the water molecules displaying cohesion so that the water doesn't pop out and spill everywhere. And sixth is polarity. Now, hydrogens have a positive charge and oxygen has a negative charge. So when you put them together to make H2O, there is a positive side and there's a negative side. Hence, they are polar. They have a property of polarity. Now, next, we have the different types of solids. There's only two, crystalline and amorphous. Crystalline solids are highly ordered, repeating structures. So you'll see patterns appear again and again and again and again. So, for example, a pattern would be 1, 2, 3, 1, 2, 3, 1, 2, 3. Or you see this shape, this shape, this shape, this shape. There's an order. Unlike with amorphous, it's discombobulated. It's disconjunctioned. It's disordered. There's no pattern. It's all random. It's a mess. So that's what amorphous is. Over here, we have the changes of the the phases of matter displayed with water. So you can see that there's sublimation, condensation, freezing, melting, deposition. Just familiarize yourself with it. Now, it's an important thing to note this is because we need to find out the processes, the specific processes. And I'm not talking about melting or freezing, I'm talking about the exothermic and the endothermic processes. Now, the exothermic process is a process that releases heat from the substance. So, for example, would be freezing. For an object to freeze or a substance to freeze, if water were to freeze, it needs to release heat for it to get colder. Or burning. Anything that releases heat is considered exothermic. So if you're to have a newly cooked chicken, okay, past tense, cooked chicken, and you could see the smoke come off, you could say it's exothermic because you could see it release heat. Now, an endothermic process is a little bit of the opposite. This requires heat to be added to the substance. So, for example, an ice cube melting is considered endothermic because heat is constantly being added to the ice cube for it to melt. Other examples could be cooking or evaporation. Anything where heat is being added to the system or the substance. That is an endothermic. So again, an exothermic process, heat being released from the substance, burning, freezing, condensation, etc. Endothermic process, heat being added to the substance. So that's melting, cooking, evaporation. Next, we have solutions. Now, solutions are just a mix of two or more different substances. What I had earlier, which was chocolate milk, is considered a solution since it consists of chocolate powder and milk and ice cubes. So, when it comes to solutions, there are usually two parts. You have the solute, which is the substance being dissolved, or usually what you tend to pour in. And then the solvent, which is like the base. It's what dissolves the solute. So if you're to have a powdered hot chocolate, your milk would be the solvent because the hot chocolate, the solute, will dissolve in the milk. Or if you're going to have coffee, when you add sugar into the coffee, the sugar is a solute because it's dissolving inside the base. Now, when it comes to solute, it has specific properties. It can either be soluble, meaning it dissolves readily, like it's really easy and quick to dissolve, or insoluble, meaning it's incapable of dissolving. It doesn't mix at all. So examples of soluble substances would be sugar, salt, baking soda. They're really easy to mix. Unlike insoluble, these are substances that have a hard time. So if you were to put sand into a glass of water, that sand isn't going to go anywhere. You're going to see that sand still in. Or plastics or metals. They really won't mix well with almost any liquid. Now, another kind of solubility and insolubility is called miscible. Now, the difference is with soluble and insoluble, you're adding solids into the base, into the liquids. When it comes to miscibility and being immiscible, this refers to two liquids. So, miscibles are basically liquids that can be mixed. And immiscible means these are liquids that can't be mixed. Examples of miscible liquids being alcohol and water, acids and water. If you were to pour both of them together, they'd mix pretty well. Unlike immiscible liquids like oil and water. If you were to put oil and water together, you'd easily see the separation. Oil would go down and water would go up because oil's too dense. So that's the miscible and immiscible. It's very similar to soluble and insoluble. One talks about solids, the other talks about liquids. Next, another mixture. Now, these mixtures are called homogeneous or heterogeneous. Now, a homogeneous mixture is a combination of two or more substances that are perfectly blended, such that no individual components are visible. So, for example, blood, brass, coffee, this metal straw, actually. It's homogeneous because it is perfectly blended of steel, aluminum, iron, whatever combination of things are in here, it's perfectly blended. There's nothing that stands out. So the opposite of that would be a heterogeneous mixture, that being like a salad or a chocolate chip cookie. Now, when you try to mix a salad, you could still see the lettuce, you could still see the tomato, you could see the dressing, you could see the croutons. It's all separate. It's very obvious to see. Same thing with chocolate chip cookies. You could see the dough, you could see the chocolate chip, sometimes you can see the walnuts, depending on the recipe. So you could see each individual component. That's how you could tell if it's homogeneous or heterogeneous. Homogeneous if you cannot see any individual component. Heterogeneous if you could see it. So ice cubes in a drink, that's heterogeneous. Or, yeah, sand and water, that's heterogeneous. Now, the last few terminologies we'll need to learn is just this, concentration. So concentration refers to the measure of how much solute is dissolved in a solvent solution. So it determines how strong it is usually. Like if there's a lot of coffee or a lot of caffeine in your coffee drink, it's concentrated. There's a lot of caffeine. Now a dilute solution means there's lesser solute than the solvent. It's diluted. Like for example, if you were to put a sachet of Milo and you put in 3 glasses of water, it's diluted. It tastes mainly like water, more so than Milo, right? But if you were to put concentrated solution where there's a greater solute, that's like adding 4 packs of Milo and half a glass of water. You're going to taste a lot of the Milo and you'll probably want to add more water. Going on to the computation side of the video, we only have 5 formulas, 5 problems, one for each formula. So we have percent by mass, percent by volume, molarity, molality, and lastly, we have normality. So first, we'll start with percent by mass, which is already written here. So this is the formula. You can do times 100% just to make it easier. I don't have a calculator with me. I'm just using the answers I have in my notebook. So just double check it if I'm wrong. But anyways, let's do this. Percent by mass. So let's say we were given this. Let's say our given was 150 grams of H2O. And then we also have 155 per gram, 155 grams of sugar. Now we need to find the percent by mass. Oh, right. We also have okay, my fault. I wrote this wrongly. So this is our solution. We also have 5 grams of sugar. So originally only H2O and sugar is given. However, since these are both technically solutes, or solute and solvent, sorry. Since this is the solvent, the base, and then you have the sugar, which is the solute, the thing that's going to be dissolved, they are still a part of the solution. They are both still a part of the solution right here. So, in this case, when you add them together, that's your total solution, which is needed for the bottom part of our formula, the denominator. So we could simply just plug it into the equation here, or the formula. So the mass of our solute is 5 grams. So we're going to do 5 grams of sugar divided by the mass of our solution, which is 155 grams. 155 grams of sugar solution. Yes, I'm aware my penmanship is not the best, but you're going to have to deal with it. Okay, so then once we divide this, we can then multiply it by 100%, so it's easier to find the percentage. So we divide it, we'll then be given an answer of 0. Here we go. We're going to be given an answer of 0.0323, but then you're going to multiply it with 100%, or simply just move this 2 decimals. You'll then be given 3.23%. And that's your answer for this, percent by mass. Really easy, right? It's just division. Same thing with percent by volume. So for this problem, this time I'll write the given properly. For percent by volume, it is actually more or less the same thing. So if we move here to the bottom, so percent by volume, which I'll shorten to as vol, is equal to vol of solute divided by the volume of solution times 100%. This isn't necessary, but it's only to make it easier. So if you notice, this is like the exact same thing as the one above us, except instead of mass, we just replace it with volume. So the units are going to be different. Instead of grams, we're going to be using liters. So here's our given. So our given is 45 milliliters of ethanol, and then 125 milliliters of H2O. So first we need to get our solution, because that's what's here. That's the only thing we're missing is a solution. So we're just going to add it together. 45 plus 125 is equal to 170. So 170 milliliters is actually our solution. So this is our solute. This is our solvent. And then let's just do, I don't know what this is. I don't know what to label it. Let's just say it's our solution. I don't know if I should call it the ethanol mixture, but yeah, it's a solution. So now that we know what this is, we're simply just going to plug it into the formula, the equation. My goodness. So you could convert it to liters. It should give you the same answer, but in my notebook I didn't, so I'm just gonna trust that my old self knew better. So we just put it in as 45 milliliters, which is the solute again, divided by the solution, which is 170 milliliters, times 100%. So you're gonna cross out the milliliters, and then when you divide it, you should be given an answer of 0.2647 times 100%. Again, move 2 decimals. You'll then be given 26.47%. That is your percent by volume. So just to be clear, this means that 26.47% of the solution is ethanol in terms of volume. And then in terms of mass, the one up here, 3.23% of the sugar solution is made of sugar. So that's already our second formula. Our third formula is going to be molarity. So this is often represented by capital M. So molarity is equal to moles of solute divided by liters of solution. So now we're gonna talk about moles again, mole ratio, throw back to first quarter and second quarter. So here's a funny thing. All of these formulas just revolve around division. It's just you're replacing what's on top and what's at the bottom. Okay, so for this problem in molarity, this is what we're given. We're given, what are we given? Hold on. I'm a little confused as to what my notebook self wrote. Wow, what did I do? Oh, okay, I know I did. Okay, so our given is 2.4 grams of NaCl, and then 40 milliliters of whatnot. So this is going to be our solute, and this is going to be our solvent. Sorry, our solution rather. This is going to be our solution. I am dumb. Okay, so first we're going to need to find the mole ratio. So we're going to get the mass of NaCl. First, we're going to need a periodic table, but since I don't have one, I wrote it down in my notebook. So Na, or sodium, has 23 grams. Okay. And then chlorine, Cl, has 35 grams. And since there's only one atom for each, you simply just add it together. You'll be given 58 grams per mole. So now that we know how many grams are per mole, we can then use the mole ratio to find out how much moles is 2.4 grams. So we're simply just going to do some simple conversion. 2.4 grams of NaCl times 1 mole of NaCl over 58 grams of NaCl. This will equal to 0.04 moles. Okay, so now that we have our moles, we can then convert our milliliters into liters, which is straightforward, which is basically just 0.04 liters. So now we're just going to plug in the values into the equation. Very straightforward. So our molarity, M, is equal to moles of solute, 0.04 mole of NaCl divided by 0.04 liters, meaning that our molarity is equal to 1. Also, molarity can also be expanded into 1 mole per liter. That's what molarity is. Next, we have molality, which is a bit different. Now, the only difference with molality is instead of doing liters of solution, it is kilograms of solvent. So in this case, it is basically small m this time, so it doesn't get confused with molarity. Small m is equal to moles of solute again, and then kilograms of solvent. Okay, I do not have a calculator with me, so I'm just going to use the same problem as this. It's pretty straightforward, but I'll just show you the process again for this because I don't know if I have the exact same thing. But just keep in mind, the difference between molarity is that it is moles over liter. The difference with molality is it's moles over kilograms, okay? So if I were to have the same values as this, just for the sake of simplicity, let's say we'll have 0.04 mole again of NaCl. And then we also have let's say 0.04 kg of whatever solvent, let's say it's H2O. Your M is going to be equal to 1, as you can see. So it's a small m. Keep that in mind, small m. So this can also be turned into 1 mole per kilogram. It can be turned into that, converted into that. So just keep that in mind. And then lastly, we have normality. Here's an example. Let me take my phone off of the stand. So again, so normality is here usually used with acids. So there are two formulas. This one is the shorter one. Normality is equal to molarity times N, which is the total positive oxidation number, or basically the total numbers of positive H and hydroxide. So, for example, in these compounds, you could see that there are 2 hydrogens, meaning that the N is equal to 2. In this one, you have you have NaCl. Hold on. And since it has a positive charge, the N is equal to 1. Wait, I'm getting confused here. And then with this, you have aluminum, usually metal, aluminum. So you're just going to multiply the 3 here, the positive 3, because aluminum has a charge of positive 3. Multiplied with the atoms here, you're going to get a number of 6. OH, there's a 1 here. Magnesium plus 2. So just keep that in mind. It's more focused on the positive charges. Metals count. It doesn't necessarily just mean hydrogen and hydroxide. Metals can count too, as you can see from these examples. So here's an example for this. So let's say we're just trying to find the normality like this. We already have our molarity. We just don't know our small n. So our small n here is 1 because there's only a hydrogen here. So 2m times 1 equals 2n. Now we have another formula, which is normality is equal to the number of equivalent weight over liters. And the number of equivalent weight is equal to mass over equivalent weight. And then equivalent weight is equal to molar mass over small n. So to do that, it would be like this. So let's say we have 5 grams of H2SO4 in 200 milliliters. So first we get the molar mass by finding the atomic mass for each element. We added it up and we got 98 grams per mole. We found the small n being 2 since there's only 2 hydrogens. So we added it and plugged it into the equivalent weight, which again is this formula, molar mass over n. So we have the molar mass, which is 98, divided by 2, which we got 49 grams. That is our equivalent weight. Then we use this formula, the number of equivalent weight is equal to mass over equivalent weight. So we got the mass, which was given, 5 grams, and then we divided it by 49. This equaled to 0.1. So after we got that, we did the final formula, which is the number of equivalent weight over liters. So we plug that in. 0.1 is our number of equivalent weight, and then the liters being 250 milliliters, which can be rewritten as 0.25 liters. So I put it here, plugged it here, and this was our final value of n. 0.4 normality, or number of equivalent weight over liters. And that is literally everything you need to learn in chemistry. So yes, thank you for watching, and I'll see you in physics.